So one thing that's different in this graph is we're given a domain. We're not going to graph the whole thing over and over and over again. We're just going to graph what this looks like between 0 and 2 pi. Anytime that you're given a domain, you're going to add 2 more key points that you're going to label on your graph. Those key points are the endpoints. So you're going to graph the endpoints. What happens when x is equal to 0? What happens when x is equal to 2 pi? And in this case, when you plug in 0, I hope you can see right away that you would have gotten 0. And when you plug in 2 pi, you're going to have to ask yourself, what is sine of 2 pi? It's equal to 0 as well. So in this case, our endpoints also happen to be intercepts. So we would have found them naturally when we did our first step. Which is finding our intercepts. But there are some cases where your endpoints aren't your intercepts. They're going to be off in the middle of nowhere, so you'd still need to label them. As far as finding our intercepts are, when you set x equal to 0, you get y equal to 0. So 0, 0, which we already knew as one of our endpoints, is our x-intercept and our y-intercept. If you want to find your x-intercepts, by setting y equal to 0, again, it's going to happen when x is equal to 0 or when sine x is equal to 0. How many times is sine x equal to 0 from 0 to 2 pi? It's at 0, at pi, and at 2 pi. Of course, we already figured out 0 and 2 pi, but now we know that we also have an x-intercept at pi. We're not dividing by 0. As x gets really, really big, there's going to be no asymptote at 0. In fact, it's just going to keep oscillating like a sine curve, but get bigger and bigger amplitudes as you go along. So if we analyze this function a little bit, what's happening? We've got a sine curve, which you know is periodic and keeps going on forever. But as x gets bigger and bigger, this value in front is going to change its amplitude. So its amplitude is just going to get bigger and bigger sine curves as you go out with larger and larger amplitudes. So this one will have no asymptotes. It will have, because it's a sine curve, lots of maxes and mins. So we will have stationary points and inflection points. So our first derivative. Product rule, keep one the same. The derivative of sine is cos, plus keep the other one the same. The derivative of x would just be 1. You don't have to write the 1. It's just nice because I was talking about doing the derivative of the other one, so When is this equal to 0? Well, this is where you're going to have to go to our calculator, because how do we solve this? If we were trying to solve this without our calculator, the problem is that we have both sine and cos. You can't write it as a single function. You've also got an x involved there. So how do we figure this out? Let's go to our calculator. If we type in x, is it x cos x, sorry? X cos x plus sine x. So that's my function that I want to graph. I want to look at this window because we're only looking at from 0 to 2 pi. So I'm going to change my x minimum. I'm going to go from -1 just so I can see my y-axis up to 2 pi. My graph is currently set to go from, oops, -2 pi. My graph is currently set to go from y min to y max of -4 to 4. So this is what it looks like. This is the graph of my derivative. So what I just did is I just graphed this. I want to find out where it's equal to 0. How am I going to do that on my graph? I need to find out wherever there are x-intercepts. We already know this one at 0. But let's find that second one. So second, calculate. We want to find number 2, the 0. If you move the cursor to the one you want to find, it says go to the left of it. So hit the left key a couple times until you're to the left of it. Then it says go past it and go to the right of it. My calculator shows dotted lines to show which two values I'm checking in between. Is our x-intercept between those two? Yes, it is. So when I push enter on the guess thing, it figures it out to be 2.03. So one of them is x equals 0. One of them is x equals 2.03. And the other one, second, calculate the other 0. Now, on my graphing calculator on the screen, sometimes if I hit the arrow key too fast, too many times, my whole thing freezes. So I'm going to show you a shortcut that you can also use. So instead of having to click all the way to get to the left side, I already know this one was at 2.03. Now I want to pick a value left of this one and right of that one. I'm going to guess that 3, I just typed in 3, is left of it. How did I do? Good. Can you see that that dotted line is left than this x-intercept? I know that my window went to 6.28. So for my right bound, I'm going to type 6.25. That should be pretty close to the right of it. Sure enough, there it is. Is my x-intercept between those two lines? Yes, it is. So when I push enter on guess, it finds it for me. That is often a lot quicker than pushing the arrow keys like crazy over and over again. 4.91. So we've got 0, 2.03, and 4.91. Now, as far as plugging things back into this equation, since we just graphed it, what's happening between 0 and 2.03? Is the derivative positive or negative? It's positive. And then between 2.93 and 2.03 and 4.91, it's negative, and then positive after that. So because I graphed this, I already know that it's positive, then negative, then positive. I don't have to plug in the values because I had my calculator to help me figure that out. So I now know from calculus that I'm going to have a maximum at 2.03 and a minimum at 4.91. For my second derivative, for figuring this out, well, we're going to have to do the derivative of x cos x. So that's going to be a product rule. Keep one the same, derivative of the other one. plus keep the other one the same, derivative of the first one. Then plus we have to do the derivative of sine, which is cos again. Again, to figure out where that is equal to 0 is not going to be easy. And cos x plus cos x will be 2 cos x. Two things I can do for this. I could retype that equation in and find the x-intercepts of that one. How could I find them from this graph? They're going to be the max and the min of this graph. Okay? So if I wanted to find that maximum, second calculate, number 4 maximum, between 0 as my left bound and 2.03 as my right one, I'm going to find out that one of them is going to be at 1.07. And my minimum from this graph, second calculate, number 3 the minimum, I know that there's going to be one left bound if I pick 3 and a right bound of 5. Push enter at 3.64. .07 and 3.64. Again, you could type this into your graphing calculator. If you did, these would be the x-intercepts. If you typed it into your graphing calculator and had those as your x-intercepts, you'd also be able to easily tell where it was positive and where it was negative. I'm going to push in your brain right now a little bit. And we have the derivative graph here. According to the first derivative graph, if this is the maximum and this is the minimum, is the second derivative positive or negative before that maximum? It's going to be positive. Why? Because the slopes are positive. And then in between the maximum and the minimum, your derivative function is decreasing. So that would tell you this is negative. Right? And then this is increasing again, positive. I kept them as lines because that's what, I'm going to change them to curves in a second. But I kept them as lines because that's what's showing here. Increasing, then decreasing, then increasing. Because I'm going from my derivative graph to my second derivative graph. And whenever you just move one derivative graph, that's like doing your first derivative where it's increasing and decreasing. Now that we've figured that out, I can go back here, take away those arrows, and say this is going to be concave up, this is concave down, this is concave up. So that's going through the entire process of all of our derivative stuff. And now when we go to graph this from 0 to 2 pi, things that we know that we have x-intercepts at 0, pi, and 2 pi, and 0 and 2 pi are our endpoints. This is pi right here in the middle, which is roughly 3.14. We know we have a maximum at 2.03, and we have a minimum at 4.91. We also know that we have an inflection point at 1.07 and at 3.64. You can plug those back into the original equation to find out where they are. what I'm going to do right now is show you how you can plug in multiple values quickly so that you don't have to do them each individually, and hopefully that'll be a little bit faster. Okay? So I'm going to go back to my graphing calculator. I'm going to go back to y equals. I'm going to delete the derivative graph that we had. Okay? I'm going to delete the derivative graph, and I'm going to type in the function that we originally had, which was x sine x. I should have checked that we were in radians to begin with, and we were. Otherwise, everything we would have done so far would have had to been thrown away. Okay, so it's good. And now I'm just going to hit graph and see what this actual function looks like. Does it look like we have a maximum around 2.03? Whew, I might change my window here just so that I can see that minimum. I'm going to change my y min to -7. See if that's enough. Great. So, how do I find those coordinates quickly using the graph instead of having to type them in each individually? If I go to second, calculate, the very first thing is value. So if I want to find the value when x is equal to 2.03, I just type in 2.03, push enter, and it finds it. It's 1.82. Once you do one value, you don't have to go second, calculate again. You can just go 4.991 right after that. There's our minimum at -4.81. Let's find those inflection points. 1.07. Whoops. Did I do 107? 1.07. There's our one inflection point at 0.94. And 3.64. See how quick that is as far as plugging things in? A lot nicer than having to type in each one, -1.74. So, as far as putting some of these points on, 2.03, 1.82. That would go about there. 4.91, -4.81. That would go about there. Inflection points at 1.07.94. And 3.64, -1.74. This is going to be concave up. This section is going to be concave down until here, and then after this, concave up again. That's an endpoint, so we just stop there, and this is our final graph. So what I did with this is I followed the process all the way through. I will tell you this much, though. If you are given a graphing question on a calculator part of an exam or a calculator part of a test and it says you can use your calculator on this, unless it explicitly says show all the first derivative and second derivative, it would not be wrong if you immediately went to your graphing calculator and drew the graph. So if you went to your graphing calculator and drew this graph, instead of using the first derivative, you could have found your maximum right away from going from 1 to 3 and got that maximum at 2.03, 1.82 that quick. And that would be fine. And you could have found your minimum really easily as well. And you could find all your x-intercepts really quickly. The thing that would be hard to find is you still need to do some calculus to find those inflection points. So if you wanted to label those inflection points, if the question says, use your calculator, find the inflection points, then we would have to go through what we did there to do our first derivative and either graph it and find it from that graph to figure out those inflection points. But if you have your calculator, some things can be done a lot quicker just by getting them directly. And that is still an important thing to know on an exam. When can I do what in the fastest way possible? On some sections, I give a calculator and a non-calculator, yes.